Hello class, welcome back. This tutorial will introduce the support vector machine regression and classification model, and also the neural network regression and classification models using the multi-layer perceptron model. And we will also use the insurance dataset we used in our last tutorial for building the regression models. And on the other hand, we'll use the income dataset that we used in our decision tree model for building the classification models. And we will also introduce two different approaches for conduct a threefold cross-validation evaluation. Well, let's first import our insurance dataset. And we will then recall the structure of our dataset. So if you still recall, in total we have 7 different variables. The variable expenses is considered as our target variable, and the rest 6 variables are considered as predictors because this expenses variable is a numeric variable, which means it's a number. So we will need to use a regression model to predict the health expenses in the future. And we will first split our data set in a simple way. We will use 50% of the instances to construct the training data set, and for the rest 50% of the data set, we will further partition them into 20%, 25%, and 25%. As testing data 1, testing data 2. So let's run this chunk. Well, we have repeated this process like 3 times already. And here we will first build a support vector machine regression model. Well, this model is in the library, in the package curlab. So we'll first load this library, and then we will build this model using key SVM model. And similarly to the decision tree and Bayesian Bayes models, well, this is our target variable, and we use the dot to represent the rest variables as predictors. And we use the training dataset to build this model. And support vector machine include many different kinds of kernels, and here we use one of them called rbf.kernel. And here we see a parameter c. Well, the effectiveness of a support vector machine is based on the kernel, the selection of your kernel, and the kernel parameter, and also the soft margin parameter c. Well, if you have a small value for this parameter c, the training error will increase. We will have a larger training error. But if you have like larger value for this parameter c, your model will be more easily to overfit. So here we use the default value c equals to 1, and then we build this model. Well, you can always use this question mark and the model name it will show you all different kernel names and all the parameters and all kinds of models. And next, in order to predict and evaluate the performance of our support vector machine model, we still use this predict function and also M metric. Well, because this one is a regression model, so instead of using accuracy, precision, and so on, we will still use these 6 different type of error measures and correlation and R-square measures. So let's predict the result on our text data 1 and text data 2. So you can see the R-square for both the testing data sets reaches 82%, around 82%, which means this model can explain 82% of the variance for our testing dataset. And the correlation is pretty good, which reached to 0.90. And next, we will build the neural network models. We will use the multi-layer perceptron models from RWACA to build our neural network models. Well, we need to first load our RWACA model, and then using this make WACA classifier to locate and simplify the name of this model. And notice that there are a few different parameters that are required in our neural network model, this multi-layer perceptron model. The first one is learning rate. The default value is 0.3. And the next one is n, which is the number of the epochs with default value 500. And another parameter is h, which is a hidden layers to be created for this network, and the default character is a. Well, there is another parameter called m. M stands for the momentum. So it is the momentum rate for the backpropagation algorithm. And the value is from 0 to 1. The default value is 0.2. So we will build a default neural network model using this multi-layer perceptron model, NLP function. So we will also still using expenses as our target variable and the rest 6 variables as our predictors, and build this model on training dataset. So this model is equivalent to the L equals 0, with all these parameters equals to their default values. So let's build this NLP model. And then similarly, we'll also use predict function and metric function to predict the expenses for the patients in our testing dataset, and then evaluate the prediction. So we will use these four lines of arguments to predict and evaluate on both testing 1 and testing 2. So comparing to the support vector machine model, well, this model performed better on the testing 1 and testing 2 because comparing to only around 82% of variance, this neural network model can explain around 85% of variance for the testing data 1 and testing data 2, and also the correlations are higher than the correlation we use by the support vector machine models. Well, because this model is from the RWACA package, we can also use the evaluate WACA classifier function to replace both predict and metric functions. So it will directly generate the prediction and evaluation for us, but it only presents as 4 different error measures and no correlation. Oh, there is correlation, but no R-square. Well, next we will introduce 2 approaches to conduct the n-fold cross-validation evaluation. Well, it is similar to what we did before, using the for loop to generate n pairs of training and randomly select training and testing dataset, and using training dataset for training dataset to build a model, and testing dataset to predict and evaluate. And then we go through, because we generate n pairs, we'll use n iteration for n times and get the average evaluation from this n pairs of datasets. Well, similar to that n-fold cross-validation, first we need to partition the instances equally into n different collections. And then because we now have n collections, we will need n different iterations. So for each iteration, we'll use one collection as testing dataset and the rest n-1 collections as training datasets. So for example, if we use a tenfold cross-validation, we will have 10 collections of instances, and for each iteration, we will use one collection as testing dataset, and the rest from index 2 to 9 to 10. So there are like 10 collections of instances will be used as training datasets. So here we will introduce two approaches to build the threefold cross-validation. The first step is still to set seed. In order to get the random results repeatedly, consistently, each time we need to set seed. And then we use this create folds function to equally partition the instances into like how many folds you want. You set this k equals to the number. So here let's look at this function. The first parameter is the target variable we're gonna use is a y, the instance, the expenses. And the second parameter is specify how many folds of cross-validation do you need. For example, if you need like 10-fold cross-validation, you just change the 3 to 10, and it will partition the instances into 10 collections. But now we use 3, so we have 3 folds. The create folds function will generate 3 collections of instances, and we store this those are like index. We store those index into this folds variable. So let's first create folds, and then we see the structure of this folds. So you can see that it is a list with 3 elements. Fold 1, 2, and 3. So for the first fold, we have 445 elements. And the index, those index are the index of rows from the original dataset, are 3, 4, 8, 10, and so on. Those are like randomly selected. So for the fold 2, we have 447 instances. For the fold 3, we have 446. So basically, numbers of instances in each fold is similar, and then we create one list and one array to store the evaluation results from each iteration. And next is a for loop. Similarly to the for loop we used before, now inside this for loop, we'll no longer need to randomly generate using the set seed and then randomly generate the training and testing dataset, because now we already have 3 folds available. Because we wanted to build a 3-fold cross-validation as an example to show you guys. So we will need to have 3 different iterations. So the iteration number is 3. So inside each iteration, for example, if it is the first iteration, well, we will use this folds with I equals to 1. So it is the instances from the fold at index 1. So those instances will generate and construct the testing dataset for the first iteration. While we use a minus sign to exclude the fold number 1. So we will include fold number 2 and fold number 3, all the instances from these 2 folds to construct the training datasets. Well, if it is the second iteration, well, we will use the instances from fold number 2 to create this testing dataset. And the rest instances, the instances from fold number 1, fold number 3, will compose this training data set. Well, similarly, for the third, our last iteration, the instances from fold number 3 will construct the testing data set this time. And the instances from fold number 1, fold number 2 will be used to construct this training data set. So now we have both training and testing data sets ready for each iteration. We will now use the key SVM function to build our support vector machine model similarly. And we'll still use the rbf.kernel and c equals to 1. And then we will use predict and metric function to predict the expenses for the instances in our testing dataset and evaluate the model performance using the metric function. Well, we will store the 6 merit errors and correlation coefficients and the R-square values first inside this list. And then we use the cbind to append those values from this list to the array. And after 3 iterations, we will use the row means to calculate the average evaluation measures for the 6 error measures and also the correlation coefficient and R-square. And let's run this one. So after this row means, we will generate average evaluations. These are actually the average number from these three different iterations. Well, let's go ahead and introduce the second approach of generating the n-fold cross-validation. Well, the first few steps are similar to the previous approach. And instead of using the for loop, now we will introduce the function list apply. We use the list apply function to generate this n-fold cross-validation method. Well, how does this list apply function work? Well, the first parameter is a list, which in our case is a folds. Folds consist of 3 elements, fold 1, 2, and 3. Well, the second element is function with x as its parameter. And inside this function, we can see there are like the construction for training and testing data, building model and predict model, and then evaluate model, similar to the R commands inside the for loop before. And notice here, we do not have the array and list to store the evaluation values from this 6 error measures and correlation on R-square. Instead, we have a return function. So this return function will return these evaluations back to the CV results. So how does this list apply function work? They will first look at how many elements are inside this loop. So in our case, we have 3 elements, fold 1, 2, and 3. So for each element, we will have 1 iteration. So in our case, we'll generate 3 iterations inside this function. And for each iteration, they will replace this x by the elements from this list, respectively. So for the first iteration, they will first replace this x with fold 1. And then this x will become fold 1, fold 1. So the steps will be similar to the first iterations from our previous approach. So then it will return the evaluation values from the 8 different measures to the CV results. So after 3 iterations, this CV results will become a list also with 3 elements. Each element consists of 8 different measure values. So let's see the structure of this CV results. So it consists of 3 elements from fold 1, 2, and 3. And each element also consists of 8 measure values. And these are the attributes titles. So let's see. Let's see the fold 1 and fold 2 and 3. So basically, we got the same results as we did from the previous approach. And then we use the row means to combine these 3 folds, the evaluations from these 3 folds, and get the average evaluation. Well, we have already learned the 2 approaches to construct the n-fold cross-validation for the support vector machine. Now we will use these 2 approaches to build the 3-fold cross-validation for MLP, which is our neural network models. Well, the steps are the same. Besides, we just replace the KSVM by MLP. And let's run this cross-validation models. So basically, the performance of this neural network model are similar to the performance from support vector machine. Well, because this MLP model is from the RYCA, we can use a simpler way to build this n-fold cross-validation by using this evaluate YCA classifier. So first, we still need to use this make YCA classifier function to identify, locate, and simplify the name of this model and give the name MLP. And then we will use this MLP model to create this neural network regression model. Well, see here, we just feed this model with the whole data set, the data equals to insurance, which is the whole data set, including all the instances. And then we use this evaluate YCA classifier function, giving the model based on the whole data set and the whole data set as our second parameter. But for our third parameter, we specify the number of folds equals to 3. So this evaluate YCA classifier function will automatically build the model, make the prediction based on model and evaluate the prediction. These processes are all automatically conducted using this evaluate YCA classifier. You just need to feed the number folds equals to 3, and then we will get the results. So let's see. But however, we only have 4 error measures and 1 correlation coefficient measure. Well, we use the default values for parameters L, M, and H when we build the multilinear perceptron models before. Now we want to change some of the parameter values and see their performance and their speed of executing the arguments. So the default value for the parameter learning rate is 0.3. We will reduce it to 0.1 and increase it to 0.8. So let's run the default value and then the changed values. Well, if we reduce the learning rate value from 0.3 to 0.1, you can see that the performance will be increased. However, if you reduce the learning rate, the speed of executing the R command will be increased. Well, on the other hand, if you increase your L value from 0.3 to 0.8, the performance will be hurt. However, the speed of executing this R command will be increased. Well, next, if we want to change the parameter value I'm from 0.2 to 0.05 and increase it from 0.2 to 0.5. So let's see the results. Well, similar to parameter L, which is learning rate, if you change the momentum rate, if you reduce the momentum rate from 0.3 to 0.05, well, the speed of execution will be decreased. However, the performance will be improved. Well, similarly, if you increase momentum rate, you will get faster execution speed, but the performance will be hurt. Well, next we want to try different hidden layer numbers. We want to try 0 hidden layers and 2 hidden layers. So we will use h equals to 0 and compare it with h equals to 2. So let's run these two models. So you can see that with more hidden layers, the performance will be better. However, the execution time will be larger. But if we have no hidden layer, we only have the correlation coefficients equals to 0.62, which is not very good. Well, last but not least, we will need to try different numbers of epochs. We will try n equals to 200 and n also equals to 700. So let's try these two models and see. Well, similarly, if you have more numbers of epochs, you will have better performance. However, it will take longer to execute the R commands. So it basically is a trade-off between the performance and the execution time. Well, besides changing the parameters for neural network models, we can also change parameters for our support vector machine models using 3-fold cross-validation. Well, the default value for the soft margin C parameter is 1, and we used to use the RBF dot kernel. And now we want to change the C value, reduce the C value to 0.1 and increase it to 5. So let's see. So you can see, well, if we have a smaller value for C, we will have more training errors. However, if we change, like we increase the value for parameter C, we'll have better performance. However, this model is more easily to overfit. And next, because we have many options for kernel selections, well, we used to have the RBF dot. Now we want to change it to polydot and Laplace dot. So let's try both kernels. Well, so this is the performance for the Laplace dot, and these are the performance for the polydot. So definitely there are more kernel selections. You can try them offline. Well, this is basically everything we will cover in this tutorial video. In our next video, we will introduce how to build a supported vector machine and neural network classification models. Thank you for listening. Bye.